Hello, good morning students. This is your Jagadish Kumar Bandaru. Today I am going to discuss electrostatic potential and capacitance. Second chapter in the Ncertxii textbook. This is very helpful to you to score the marks in Cbse plus 2 board exams in physics. So here I am going to discuss all the derivations from this chapter. Second chapter in our textbook volume 1. Electric potential at a point due to point charge. Here I am going to consider a point charge plus q which is at point O. I am going to imagine another unit positive charge q naught where plus q is the point charge and q naught is the unit positive charge. So what is the potential of this point charge at this point P? That is we need to calculate. So first of all I am going to consider I'm going to give a simple way how to derive electric potential at a point due to point charge. So first just I am going to consider the q naught moving from point P to point M through a distance dx. Then what is the force acting on q naught because of positive charge? Both are positive, no repulsion force. It experiences a repulsion force. Now, how much force that one? 1 upon 4 pi epsilon naught product of charges. This 1 by 4 pi epsilon naught I am going to write k. Why? Because already we know that k means 1 upon 4 pi epsilon naught. So k into product of charges q into q naught upon distance of the q naught from unit positive charge distance I am going to consider from point charge. The distance of q naught from plus q I am going to consider r. So r square, distance square. This is the force experienced by the q naught due to this point charge, which is placed at a distance r. So next one, what is the work done to move q naught charge from point P to M? Work done to move a small distance dx. My dear student, if you are going to consider here r, then this small distance consider dr. Here I am going to consider r, no, then small distance moved is dr. So then what will happen? Work done is equal to f bar dot dr bar. Then work done is equal to f dr cos theta. Here what is theta? Angle between force vector and dr vector. Both are opposite direction and angle is 180. Then cos 180 value minus 1. So here what happened? Theta value 180 and cos 180 value minus 1. Then w is equal to f dr into cos 180 value minus 1. That's why I'm going to write minus. That is the required work done to move q naught charge from P to M. To move from infinity to this point, how much work required? So I'm going to calculate total work done to move from infinity to this point. At what distance this point? R distance. Distances are always measured from this point charge only. I need to measure distances from this point charge plus q. So here I need to move infinity to R. What is infinity? Q naught is at infinity. Infinity is from point charge plus q. And what is R? I need to bring q naught charge to the point P. What is the point P distance from the point charge R? That's why I wrote R. Infinity to R. Here, this is the small work done. No? That's all. W is equal to, in the small work done, that means to move from this place to this place, this is the work done required. To move from infinity to this point, infinity to that point distance. What is the point distance here? R. From the unit positive charge distance. This is the point P I consider, no? I am going to consider this is the point P. That point P distance from the point charge is R. I am going to repeat. I need to move from. I am going to repeat. I need to move from infinity to. What is the infinity means? From the point charge, the Q naught distance is infinity. I need to move this Q naught charge to the point P. Now what is the point P distance from the point charge R? That means from infinity to R, we are going to moving Q naught charge. At the time, I am going to do, I know already work done to move dr distance. Then what is the total work done required to move from infinity to point P? From infinity to point P. Infinity to point P. Point P distance is R from the point charge. Now I am going to substituting. Already we know that dW. What is minus f dr? Minus f dr. Right. Work is equal to integral minus takeout infinity to R. What is f? Already we have the f value. This is the f value. Substitute k into q naught by r square into dr. W is equal to minus infinity into r. K q naught is constant. Take out. Better to take out from the integration. So k q naught constant. Then what remains inside? 1 by r square dr. Integrations from infinity to r. Then w is equal to minus k q naught. What is the integral of 1 by r square? Minus 1 by r. Integral of 1 by r square is minus 1 by r. From where to where? Infinity to r. Infinity to r. Integral 1 by r square formula is minus 1 by r, and limits are from infinity to r. Note down, students. So work done is equal to minus k q naught minus 1 by r whole square. Here this minus into minus plus, minus into minus plus k q naught 1 by r infinity r. First substitute the upper limit in place of r itself, minus substitute in place of r infinity 1 by infinity. Then work done is equal to k q naught into 1 by r. 1 by infinity value 0. No. Finally, what is the work done I got? K q naught upon r. So this is the work done. Total work done required to move that unit positive charge from infinity to a point r. So what is the potential? We know that potential means work done to bring the unit positive charge. Unit positive charge. From here, what is the W by Q naught? Here W, Q naught transposed to left side. Then what remains? So this is the W, Q naught transposed to the W side, work side. W by Q naught is equal to what? K Q by R. So K Q by R. So finally, we got potential is equal to simply K Q by R. This is the formula at a distance r from this charge q. This is the formula to calculate potential. What is the meaning of this? What is the meaning of this? Let us see. This is the positive charge. This is the positive charge at this point. From the positive charge, I am going to consider a point P which is at a distance r. So to calculate potential at this point, because of this positive charge, is K into this charge Q upon this point distance from the plus Q charge, that is R. K Q by R. So this is the required potential at point P because of this plus Q charge. This plus Q charge. This is the potential due to a point charge derivation. Hence proved. Note down, students. The next derivation is potential due to dipole at a point on its axis line. I'm going to consider a dipole. So negative charge, positive charge, two equal and opposite charges separated by a small distance. From center to positive charge distance L, from center to negative charge distance L. So I'm going to consider a point on the axis line. This is my point P. I need to calculate a potential due to dipole at this point P on the axis line. So this is I'm going to consider first charge. This is I'm going to consider second charge. Second charge. Because of first charge, what is the potential at this point? That is I'm going to consider V1. K times charge Q. Why? Because already we know that any point charge Q, if I'm going to calculate potential at distance R means how to calculate K into charge by distance of the point from the charge. The same logic I'm going to use in here. K into charge is Q, and what is the distance of the point from the charge? So I'm going to consider the point is at a distance R from the dipole. From the dipole means from the center of the dipole. From the center of the dipole, the point distance is R. Then what is the distance of the point from the plus Q charge? Just from the R, subtract L. You are going to get this distance. That is R minus L. That is V1 potential due to this charge at point P. K into this charge Q by distance is R minus L. And I am going to calculate V2. That is the potential due to second charge minus Q charge at point P. So K into what is the charge here? Minus Q. Students, remember potential is a scalar quantity. There is no necessity to represent the direction. Why? Because scalars has no direction. That's why while calculating magnitude, negative symbol also we need to substitute. So if it is a scalar quantity, we are not going to using symbol to represent direction. Why? Because scalars has no direction. That's why while calculating magnitude, take the quantity charge along with the symbol. So this is the negative charge means negative charge we need to take along with the symbol. I need to substitute in the formula. K into minus Q by what is the distance of the pointer from second charge, negative charge, from ear to ear R and from ear to ear L. Then what is the total distance? This is R and this is L. So R plus L is the distance of the point from the negative charge. So that's why R plus L. Total potential. This is the ordinary addition. Why? Because potential is a scalar quantity. So ordinary addition V1 plus V2. Right. V is equal to what is V1? K Q upon R minus L plus what is V2? K minus Q upon R plus L. So I'm going to take the KQ common. Then what remains here? 1 by R minus L plus into minus. Minus KQ I took as a common. Then what remains? 1 upon R plus L remains. Now V is equal to K times Q. So LCM is R minus L into R plus L. R minus L into R plus L. Now here R plus L minus R minus L. So V is equal to KQ into R plus L. So minus R, minus into minus plus L by A minus B into A plus B. A square minus B square means R minus L into R plus L, R square minus L square. Here plus R minus R get cancelled. Then V is equal to KQ times L plus L, 2L upon R square minus L square. So finally what is the potential I got? K into, we know that Q into 2L is the dipole moment P. Q into 2L is the dipole moment P. Then Q into 2L dipole moment P by R square minus L square. This is the potential due to a dipole on its axis line. Potential due to dipole at a point on its axis line. Hence proved. Where K is equal to 1 upon 4 pi epsilon naught. Remember. Note down, students. So third derivation, potential due to dipole at a point on its equatorial line. And students, I am going to consider this is the negative charge, this is the positive charge, which are separated by a distance 2L. From center to this distance is L, from center to this distance is L. And the equatorial line means a line passing through center and perpendicular to the axis of the dipole. Then this is the equatorial line. So I am going to consider any point y, which is at a distance r from the center of the dipole. From the center of the dipole. At this point I need to calculate potential because of dipole, due to dipole. I am going to consider this is the first charge and this is the second charge. What is the potential because of first charge at this point? So V1 is equal to, because of positive charge, K into charge by distance. K into charge by distance. What is the distance of the point from this charge? It is R, it is L. From the Pythagoras theorem, this is root of R square plus L square. So distance of the point from the charge is root of R square plus L square. That is the V1. Now I am going to calculate potential at this point y because of this negative charge. V2 is equal to K into, so what is the distance of point from the negative charge? Same distance. It is L, it is R, it is root of R square plus L square. Then K into Q upon, what is the distance of the point? What is Q here? Negative charge. I need to write negative charge also. Why? Because potential is a scalar quantity. So K into minus Q by, what is the distance? Root of R square plus L square. Root of R square plus L square. So what is the total potential at point y? Total potential at point y, that is V1 plus V2. V1 is K times Q upon under root R square plus L square, plus V2 is K times minus Q times root of R square plus L square. So that is V at potential at point y. So finally K into Q by root of R square plus L square, plus of minus minus, K into Q upon root of R square plus L square. Both are same. So finally we are going to get, both are same, we are going to get 0. So potential at any point on its equatorial line is 0, no doubt at all. So that's why, what is the conclusion? Because of dipole, I am going to consider potential due to dipole at a point on its equatorial line is always 0. 0. Hence proved. Note down, students. Students, this is the fourth derivation, potential energy of system of two charges. So I am going to consider there are 2 points. One is A, another point B. I am going to bring Q1 charge from infinity to point A. Then how much work we need to do? Work. Already we know that potential is nothing but work done by unit positive charge. So from here, what is the work done? V into charge. V into charge. So what is the potential? Work done per bringing charge. Here work done is equal to V into Q. Like that, I am going to calculate what is the work done to bring this charge from here to here. What is the potential at this point here now? Why? Because there is no charges here. Here there is no charges. At point A, at point B there is no charges. In the absence of charges, no fields, no potentials. So now I am going to bring Q1 charge from infinity to this point. Then I need to do some work. How much work I need to do? Potential at this point VA and bringing charge Q1. What is the potential at point A initially? There is no other charges here in this region. So potential at A is 0 only. Then what is the work done required? Work done is equal to VA 0. 0 into K1 0. So work done required is 0. Okay, right. I brought Q1 from infinity to this point A. Now, because of this charge in this region, point B has the potential. I am going to consider point B distance from point A is R. Then what is the potential at this point B because of this charge? Already we know that potential at point B I am going to calculating because of this charge. Because of this charge there is a potential. How much? K into this charge Q1 upon charge distance from the point is R. That is the potential at point B. Now what is the work done to bring Q2 now? Q2 charge from infinity to point B. I am going to calculate work done. This is the work done to bring the Q1 charge, that is 0. Now I am going to calculate work done to bring the Q2 charge from infinity to point B. So then what is the potential at point B? VB into bringing charge is Q2. Potential at that point and bringing charge. So potential at point B is VB and bringing charge Q2. Now W2 is equal to, what is VB? K Q1 by R into Q2. Finally, what is the total work done to bring both charges Q1 and Q2 to form a system? So total work done we did is W1 plus W2. So W1 is 0, W2 is K into Q1 Q2 upon R. Then W is equal to K Q1 Q2 upon R. This work done required to form a system here, to bring these two charges from infinity to here to form a system. So this work done stored as a potential energy in the system. That's why how much potential energy stored in the system? Equivalent to this work done. Then what is the potential energy of the system? Equivalent to work done, I said no. That's why K times Q1 Q2 by R. So this is the potential energy of the system of two charges, my dear students, where K is equal to 1 upon 4 pi epsilon naught. Hence proved. Note down, students. Fifth derivation. Capacitance of a parallel plate capacitor. Capacitance of a parallel plate capacitor. I am going to consider a parallel plate capacitor. So both plates are parallel. And these are the plates. There is a plates like this I consider. Plate I am going to consider like this. Both plates. Both plates. So one plate considers positive charge, another one negative charge. Area of the plates is A. Each plate area A. Then what is the surface charge density of the plate? Charge per area. Charge per area. What is the electric field between the plates? What is the electric field between the plates? Sigma by epsilon naught. So electric field, here there is an electric field from positive plate to negative plate. Electric field will be present. That electric field value is sigma by epsilon naught. And separation between the plates I am going to consider D. Then what is the potential difference between the plates? Electric field times D. So how to calculate potential difference between the plates? Electric field between the plates into separation between the plates. That E into D will give the potential difference between the plates. Then V is equal to, what is E? Sigma by epsilon naught into D. V is equal to what? E means sigma by epsilon naught into D. That is V. That is V. And we know that sigma means what? Sigma means what? Q by A. Sigma means what? Q by A. Write down here. V is equal to, sigma means what? Q by A. So Q upon A. But already in denominator epsilon naught is there. Into D. Into D. And what is the capacitance definition? Q by V, charge per unit volume. Charge per unit volume. Capacitance we are going to define as charge per unit volume. So C is equal to Q by V. Q by V. So observe from here, Q by, what is V here? Q by A epsilon naught into D. Q by A epsilon naught into D. The same thing I wrote here. So C is equal to Q. A epsilon naught goes to numerator. What remains in the denominator? Q times D. Q cancel. Then C is equal to what? A epsilon naught by D. That is only I am going to write as epsilon naught times A by D. So what is the capacitance formula? Epsilon naught A by D. Where what is the epsilon naught? Permittivity of the medium. And A is the area of the plate. And D is the separation between the plates. So this is the formula for capacitance of a parallel plate capacitor. C is equal to epsilon naught A by D. Hence proved. Note down. Next, sixth derivation, combination of capacitors in series. If I am going to consider three capacitors connected in series, of course, to a cell, of voltage V, capacitance C1, capacitance C2, capacitance C3. In series combination, charge is the same on all the capacitors, plus Q minus Q, plus Q minus Q, plus Q minus Q. So, negative plate of first capacitor connected to the positive plate of the second capacitor, negative plate of the second capacitor connected to the positive plate of the third capacitor. Such a combination generally we call it as a series combination of capacitors. So I'm going to consider C1, C2, C3 be the capacitance of three capacitors. In series combination, capacitance, each and every capacitor will have the same charge. Suppose it consists plus Q and minus Q means what is the charge of the capacitor means Q. What is the charge of the capacitor means Q. Q is the charge of the capacitor means what is the meaning? Plus positive plate as plus Q, negative plate as minus Q. That is the meaning. So if I am going to consider the equivalent figure, by removing all the three capacitors which are connected in series, replace it with a single capacitor. It is called C equivalent in series combination. That's why I'm going to represent here S. What is CS? Equivalent capacitance which are connected in series. Equivalent capacitance of these three capacitors which are connected in series. That is CS. And I'm going to connect it to the same voltage V. Means same cell V. Now, in series combination, remember students, the resultant capacitors equivalent of these three also will have the same charge. That means this is also plus Q and this is also minus Q. Same charge Q only. Individually, each and every capacitor will have the same charge. The equivalent capacitors also will have the same charge in series combination of capacitor. And potential will be distributed among the three capacitors. I am going to consider potential across first capacitor V1, second capacitor V2, third capacitor V3. Then what is the total potential here? V1 plus V2 plus V3. Now, we know that Q is equal to Cv. From here, what is V? Q upon C. What is V? Q upon C. So, if I am going to consider what is V here? Q upon C. V means what here? This voltage V, and that means this voltage and this voltage both are same. Why? Because same voltage only. So how to write the V value here? V is equal to Q by C. No, what is Q? Q by what is C here? C equivalent. That is CS. So this one and this one both are equivalent only. That's why Q by CS. From here, what is V1? So Q by C1. C1. What is V2? Q by C2. What is V3? Q by C3. Now V1, V2, V3 value, V value substitute here. What is V? Q upon Cs. What is V1? Q upon C1. What is V2? Q upon C2. What is V3? Q upon C3. Finally, take the Q common from the right hand side and cancel out both sides. Then what remains? 1 by Cs is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. This is the equivalent capacitance formula when three capacitors are connected in series. Hence proved. Hence proved. Note down, students. What are the points we need to remember in series combination? First point, Q is the same individual capacitors and equivalent capacitors also. On the equivalent capacitance also, Q is same. Next one, potential, total potential we are going to get the sum of the potential across the each and every individual capacitors. And the equivalent capacitance, how to calculate? 1 upon Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3. These are the 3 points we need to remember in case of combination of capacitors which are connected in series. Next, seventh derivation, combination of capacitors in parallel. I am going to consider 3 capacitors connected in parallel. These are capacitors C1 and the plus Q1 minus Q1. And this is the capacitor C2 and its charge is Q2. That means plus Q2 minus Q2. And the capacitor C3. Capacitor C3. So, it consists a charge Q3. That means what? Plus Q3 minus Q3. So all the positive plates connected at one point, all the negative plates connected at another point. Such a kind of combination, that means all positive plates connected at point A, all negative plates of the capacitor connected at point B at the same point. Positive plates connected at the same point, all the negative plates also connected at same point B. So such a kind of combination we call it a parallel combination. So I am going to connect a cell. In the parallel combination, V is same, potential is same. Means here voltage of the cell I am going to consider V. Then the positive terminal connected to point A, this is a positive potential. The negative plate connected to point B, this is the negative potential. Here V means what is the potential difference between A and B? Same plates, no? So same potential difference V only. What is the potential difference between A and B? Between A and B, V only. Between A and B, what is the potential difference? V only. Why? Because A connected to positive plate, B connected to negative plate. Negative plate, V only. So, what is the potential difference between the first capacitor C1? That is also connected between A and B only. So, V only. Second plate also connected, second capacitor also connected between same points A and B. So, what is the potential difference across the second plate, second capacitor? What is the potential difference across the second capacitor? V only. Third capacitor also connected between the same 2 points A and B. Then what is the potential difference across the third capacitor? V only. That means all the plates will have all the capacitors across all the capacitors potential difference is V only. Across all the capacitors potential V only. Not only that, cell voltage also V only. So if I am going to consider the equivalent figure, that means by removing all these three, connect a single capacitor which is equivalent to, which are connected in parallel. That is I am going to consider Cp. Then what is the charge present on the capacitor Cp, which is the equivalent of all the three capacitors which are connected in parallel. So we are going to get the charge on this capacitor is Q is, I am going to consider Q. That means this is the plus Q, this is the minus Q. But this Q is not same as here. We are going to get this Q by adding these three charges. What is the charge on the first capacitor? Q1, on the second capacitor Q2, on the third capacitor Q3. By adding these three charges, I am going to get Q. That Q only present on this capacitor plates of capacitance Cp. Of capacitance Cp. And what is the voltage? V. What is the voltage? V. Here, what is V? We know that Q is equal to Cv. From here, Q is equal to Cv. That is already we know that. Already we know that. So we know that what is the, by adding these three charges, I am going to get this charge Q. What is Q here? Q is equal to Q1 plus Q2 plus Q3. That is the total charge on the equivalent capacitance. Q is equal to Q1 plus Q2 plus Q3. From here, what is Q? What is Q? Q is equal to Cv, no? So Q is equal to C. C means what? Cp into V. This is the Q is equal to Cv. Q is equal to what? Cv. Here what is C? Cp, equivalent capacitance of these three capacitors which are connected in parallel. That's Cp into voltage of cell. Why? Because across the equivalent capacitance also same potential V is present. What is the potential present in each individual capacitor? Across the individual capacitor, potential is V. Not only that, the equivalent capacitance of these three which are connected in parallel also will have the same potential V only. That's why I wrote what is Q here? Cp into V. Cp into V. That's why this V and this V both are same only, remember. This V and this V both are same only, remember. Then what is V here? From here what is V? V is equal to Q upon Cp. From here what is V? Q upon Cp. Cp, right. What is Q here? What is Q here? Q means here. Here what happened? First of all Q1. Q1 is equal to C1V. What is Q2? C2V. What is Q3? C3V. So we have the Q value from here. What is Q value from here? From here CPV. And Q1 value C1V. Q2 value C2V. Q3 value C3V. Substitute all these three values or four values here. Q value CPV, Q1 value C1V, Q2 value C2V, Q3 value C3V. Take the V common from the right hand side and cancel out both side V. Then what remains? Cp is equal to C1 plus C2 plus C3. This is the equivalent capacitance of three capacitors which are connected in parallel. In parallel. Hence proved. Hence proved. Note down, students. Here what are the points we need to remember? First point, V is same, potential is same. Means across the individual resistor and across the equivalent capacitance of three which are connected in parallel also, that is Cp. Across Cp also same potential V only. Second one, what about the charge? We are going to get Q1 plus Q2 plus Q3. This is the charge on equivalent capacitance Cp. That is, we are going to get the sum of the individual charges present on each and every capacitor. Third one, equivalent capacitance value. Simply addition of three individual capacitors will give the equivalent capacitance which are connected in parallel. Cp is equal to C1 plus C2 plus C3. That's all. These are the 3 points we need to remember in combination of capacitors in parallel. Eighth derivation, expression for energy stored in a capacitor. Suppose I'm going to consider a parallel plate capacitor. Its charge I'm going to consider that capacitor plate consists charge Q, that is plus Q and minus Q, and we know that what is the potential difference between the two plates, charge by capacitance, charge by capacitance, that is the potential difference between the two plates, right. Here I'm going to consider what is the work done required to give the additional charge dq. I'm going to consider what is the work done required, the additional charge dq. Work done is equal to potential into given additional charge. Generally, potential means the basic definition, work done by charge. From here, work done is equal to potential into charge. Here, to give the additional charge, let dq be the additional charge. Given to the plates, given to the capacitor plates. What is the work done required for that? dW is equal to vdq. So to give the total charge Q, what is the work done required? The work done in giving charge Q is how to calculate. Integral of this work done, that's all. To give the small charge dq, what is the work done required? dW. To give total charge Q, what is the work done required? Integral of that small work done. Then work done is equal to integral, what is dW? V dq. W is equal to, what is V? What is V from here? Q by C. Substitute here. Integral V means Q by C into dq. So W is equal to C, denominator C constant, take out, capacitance constant, integral Q dq. C constant, my dear student. Actually, charge and V both are directly proportional to each other. There the proportionality constant is C. Capacitance is the proportionality constant. That's why the capacitance does not depend upon these potentials and charges. Remember, my dear student, the capacitance only depends on dimensions only. This is like in current velocity, R is equal to rho into L by A. Here what is rho? Proportionality constant. Why? Because R is proportional to L, R is inversely proportional to A, and R is proportional to L by A. By replacing proportionality symbol, we are going to get the rho. That is the proportionality constant. That's why this proportionality constant does not depend upon the length and area of cross sections. Similarly, here C is also proportionality constant in this relation. Or Q is directly proportional to V. Here Q is equal to CV. Here this C is the proportionality constant. That's why C does not depend upon V. Remember, my students, C is a constant only. So C does not depend upon the V's and Q's. C is a proportionality constant. Then C depends upon what? Only dimensions. Already we derived. What is that? Epsilon naught A by D. So C depends on only medium and the area of the plates and the separation between the plates. That's all. Only dimensions and the medium present between the plates. That's all. C is a constant here. Then W is equal to, C does not depend upon Q, and V also, of course. Formula seems to be like that, but that is the proportionality constant, that it does not depend upon the V's and Q's. So 1 by C is equal to integral Q dq. What is the integral Q dq? So 1 by C, this is integral Q dq is Q square by 2. Q square by 2. Integral of x dx is x square by 2. Like that, Integral of q dq, q square by 2. Q square by 2. Note down, students. Here I use the formula integration. Integral of x dx means x square by 2. Integral, that formula used here. So work done is equal to what? 1 into q square. Q square upon c into 2. 2 times c. So this is the work done required to give the charge q on the capacitor plates. This work done stored as a potential energy or simply energy. Whatever we are going to consider, this work done is stored as a energy. Stored as a energy. Let's say what is the energy stored? This work done is stored as a energy. Then what is the energy stored in the capacitor now? Equivalent to work done. This is the work done to give the charge q onto the capacitor plate. Total work done to give the charge q onto the capacitor plate. So that work done stored as the energy in the capacitor plates. Then u is equal to what is work done? Q square upon 2c. Q square upon 2c. What is the work done? Q square upon 2c. Already we proved here. So this is the potential energy stored in the capacitor plates. And this is one formula. Next formula for energy stored in the capacitor is, we know that Q is equal to Cv. Substitute in place of Q Cv. Then Q square means what? Q means Cv. Q square means C square times V square upon 2C. C get cancelled in C square, C times. Then what is U? CV square by 2. That is only we are going to write of CV square. This is one more formula or one more expression for energy stored in a capacitor. And one more relation also there. U is equal to of CV square I am going to write as C. V square means V into V. V square means V times V. U is equal to of into what is C times V? Q. Write down in place of CV Q into V. So this is also one more expression for energy stored in a capacitor. Note down, students. Derivation 9. Expression for energy density of a capacitor. Energy density, generally we are going to represent it with a symbol small u, and it is nothing but energy stored in a capacitor per unit volume, or simply volume. So if I am going to consider the capacitor plates like this, where the energy will be stored between the capacitor plate in the electric field. What is its value? What is its volume? Area of the plate is A and separation between the plates is D. That is only volume. What is the energy stored in the capacitor? Already we proved of CV square upon volume is A into D. A into D. Observe here. We know that capacitance is equal to epsilon naught A by D. We know that capacitance is equal to epsilon naught A by D, and V is equal to ED. V is equal to ED. Substitute these two formulas here. Of into what is C? Epsilon naught A by D into V square. What is V square? ED. V means ED. V square means E square D square. E square D square. Upon in denominator AD is there. Write down in the denominator AD. So D into D square and D square get cancelled. A cancel. Then what remains? Of epsilon naught E square. So finally, what is the energy density formula I got? Half into epsilon naught times square of electric field. This is the electric field between the two capacitor plates. This is the energy density expression in case of capacitor. Note down, students. Okay, student. In next class, I will explain current electricity. So in current electricity, all derivations in next class I am going to explain. Students, if you like my channel, please subscribe, share and like it. Thank you, students.